Okay, so what we're going to do here is review the definitions of our basic trig functions. We're going to start with angles in an acute triangle. There's a few different ways to actually define all of these 6 trigonometric functions, but we're going to start with these ones. You may already have been introduced to this idea that if you are given an acute angle that is in a triangle, then you can define the trig functions on that angle according to ratios of side lengths of the triangle. So for example, using this angle theta here, that's theta, the triangle has 3 different sides. There's the 2 legs are the sides that are adjacent to the right angle, and then the side that's opposite of the right angle is called the hypotenuse. So this is the hypotenuse. And then relative to this angle theta, there is the leg that is opposite of theta, and there is the leg that is adjacent to theta. So the sine of theta is going to be the length of the opposite leg divided by the length of the hypotenuse. So there's where sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse, so the cosine of theta would be the length of that adjacent leg divided by the length of the hypotenuse. Now, hypotenuse is always the hypotenuse. It's the side that's opposite of the right angle, but opposite and adjacent legs are relative to the angle mentioned. So here is the other angle phi, the other acute angle phi, and this side is the opposite, the side BC is the side that is opposite of phi. And then side AC is the side that's adjacent to phi. So opposite and adjacent are relative, hypotenuse is fixed. So as an example in this case, we would have that the sine of theta. Now the opposite leg is AC, and the hypotenuse is AB. Whereas the sine of phi, the leg opposite of phi is leg BC, and the hypotenuse is AB. You might try writing a few of these down as an exercise. Some of you have probably heard a little bit of a memory tool, also called a mnemonic device. I'm just going to call it a memory tool, which is often pronounced as SOHCAHTOA. SOHCAHTOA. So this says that the sine is the opposite over hypotenuse, the cosine is the adjacent over hypotenuse, and the tangent is opposite over adjacent. So, I mean, these ratios are just kind of arbitrarily defined, and so this is just a memory device to kind of keep those straight. So that gets you sine, cosine, and tangent, and then we have the secant is the reciprocal of cosine. So you can see secant and cosine are reciprocals of each other. Cosine is adjacent over hypotenuse, and secant is hypotenuse over adjacent. Sine and cosecant are reciprocals of each other, and tangent and cotangent are reciprocals of each other. So there's that. So cosecant is the reciprocal of sine, and cotangent is the reciprocal of tangent. And also, we can write the tangent is sine divided by cosine. So opposite divided by adjacent. If I divide sine divided by cosine, those hypotenuses actually cancel out. So we also have tangent is sine divided by cosine. So these are a few things that are good to remember about relationships between the functions themselves and also the definitions of the three basic functions. All right. So we should recall at some point that the angles in a triangle always add up to the same number. You should pause here to see if you could fill that in. I'm going to go ahead and fill it in now. So the angles in a triangle always add up to a straight angle. I'm going to put that down here. And if you can remember what is a straight angle in radian measure, that is pi. So it is important to get used to using radian measure. All calculus is done in radian measure. The calculus of trig functions does not work in degree measure. Or it does work, but it requires an adaptation that is a little bit messy. So anytime people are doing calculus with trig functions, they're always, always, always using radian measure. Well, I should say there are exceptions, not always, but like pretty much always. Okay, so let's look at, here's an example. I have this triangle. I am given a few side lengths, and I'm asked to find the trig values on these two acute angles. So this is, let's put these numbers in. So side AB is 5.42 meters. So I'm going to write that here. 5.42 meters. Side AC is 15.35 meters. And side BC is 14.36 meters. Okay, so it asks us to say what is sine of theta. And so if I look at that, sine of theta, there's theta. Sine is opposite over hypotenuse. It's probably worth noting. Here's the right angle, so the side opposite that is the hypotenuse. Okay, so sine theta would be 14.36 meters divided by 15.35 meters. And I think I decided I really wanted to change this to 3 decimal places for whatever reason. And so this is, when you divide this, you get approximately, I'm doing this calculation on the side, this is approximately 0.936. And there's no units on here because these meters will actually cancel out. And in general, these trig functions, the units will cancel out. You should have the same unit of measurement in the numerator and denominator so that the units do cancel out. And so what you get is just a pure number ratio. In contrast, the sine of phi, phi is at angle C here. And so opposite of our hypotenuse for that, the opposite is 5.42 meters divided by hypotenuse is 15.35 meters. Which is approximately 0.353. And again, those meters are going to cancel each other out. Okay, so take the time, why don't you take the time to write in, pause the video and write in what the rest of these 12 numbers are, and I will do the same. Okay, so here are all the values filled in. So as an example, just picking out secant of theta. Secant is the reciprocal of cosine, so that would be the hypotenuse divided by the adjacent. This is of theta, here's theta. Hypotenuse is 15.35 divided by adjacent is 5.42 meters, and so dividing that I get approximately 2.832. Okay, this also asks you to draw lines matching up equal values. And I'm going to match up equal values basically by the fact that they are calculating exactly the same ratio. As an example, here are two sine of theta and cosine of phi are the same values. Basically because both of them are something over hypotenuse, and sine is opposite over hypotenuse, but the opposite side of theta is the same as the adjacent side of phi. So sine of theta is always going to be the same as cosine of phi, where theta and phi are the two acute angles. So similarly, cosine of theta is going to be equal to sine of phi. So go through here and find the other ones that are equal to each other. And I'm going to do the same. We have tangent of theta should be the same as cotangent of phi. And the cotangent of theta is the same as the tangent of phi. And we have the secant of theta is the same as the cosecant of phi. And the cosecant of theta is equal to the secant of phi. Take a minute to think about what values are equal here. You might notice a relationship between the equal values and the function names. Take a moment to think about that before I give you the answer. You may or may not recall from geometry two angles that add up to a right angle are called complementary angles. So they add up to a right angle. So it turns out that these co-functions, the co-functions on one angle are equal to the original functions on the complementary angle, and vice versa. The co-functions of complementary angles are equal. So, and by co-functions, I mean sine and cosine are co-functions of each other. Cosine is the co-function of sine, and sine is in fact the co-function of cosine. And similarly, tangent and cotangent, secant and cosecant. So here's a question, do the units matter in the sine lengths? And I already kind of addressed this up here, that the units are always going to cancel out. So as long as you have the same unit being used in each of the side length and the ratio, those units are going to cancel out. And so if I was to scale this triangle up by 1,000 times so that the units were in kilometers instead of in meters, the appearance, the general shape of this triangle would be exactly the same, and so the ratios of side lengths would not change. And so this is how we are able to define that, the sine of the angle theta, and it doesn't matter how big the triangle is. So no, the units don't actually matter inside in the side lengths. So here's an example where we can ask to calculate the missing values of the given triangle. I would encourage you to take some time to see if you can work this out yourself before I actually work it out. So pause the video and see if you can work this out. So FE is the hypotenuse, FD is given, and we have an angle E is given. So FD is the angle that's opposite, the leg that is opposite of angle E. So I'm going to say that I know that the sine of angle E is equal to FD divided by FE, which tells me that if I want to find FE, I can solve that equation, and it will be FD divided by the sine of angle E, which is, FD is 20.36 centimeters divided by sine of 1.37. And that 1.37, since it is unitless, it is in fact given to us in radians. So I'm going to use a calculator and make sure that it is set to use radian mode. And when I do that, I get approximately 20.78. And what I have here in numbers is this is centimeters divided by a pure number, so that result is going to be in centimeters. So FE is going to be 20.78 centimeters. It does kind of make sense that that hypotenuse is longer than this longer side length, but not a whole lot longer. Okay, so for DE, now that I have that this is 20.78 centimeters, I could use the Pythagorean theorem to find DE, or I could do another trig function. Like the tangent of angle E would be FD divided by DE. So I'm going to do that. Tangent of angle E is FD divided by DE, which tells me if I want to solve for DE, that is FD divided by tangent of angle E, which is 20.36 centimeters divided by tangent of this angle, 1.37. And I'm going to again use my calculator to see this is approximately 4.14 centimeters. Okay, so it is important that we see that the hypotenuse is the longest side of this triangle. If it was not, there would be something wrong here. And you might not have great intuition. I admit that I don't have great intuition for like recognizing whether this is an accurate representation of an angle with radian measure 1.37, but I kind of believe it. I know that pi is around 3, a little bit bigger than 3, which means half pi is a little bit bigger than 1.5. So 1.37 would be a pretty big acute angle. And finally, we have E, and so we need to know that DFE plus DEF has to be a right angle. So angle DFE, let's actually say measure of angle DFE plus the measure of angle DEF has to be a right angle, which is pi over 2. So that tells us that the measure of angle DFE has to be pi over 2 minus 1.37, which is approximately 0.20 using a calculator. There are two special right triangles that are important to know about because they show up a fair amount. I have drawn them here, and I want to name them. A lot of people refer to the first one as a 45-45-90 triangle, and the second one as a 30-60-90 triangle. I will not do that because that is referring to degree measures, and I want to instigate a practice of generally sticking to radian measures in calculus. And so I'm using other words to describe these. This first one can be called an isosceles right triangle or a half square. Either one is fine. It's a half square triangle. You can kind of think of that square being completed there, or an isosceles right triangle. Isosceles means that it has the one pair of congruent sides. Right triangle means it has one right angle. Isosceles right triangle means the two legs have to be equal to each other. And the other one is going to be half of an equilateral triangle. So now if we look at these two triangles, the angles in a triangle always add up to pi. Right angle is pi over 2. So that means that these other two angles together have to add up to pi over 2. So they must be pi over 4. And if we look at the side lengths, if I call each of the legs side length A, they're going to be the same since it's an isosceles triangle. Then we can use the Pythagorean theorem to say that the hypotenuse squared is equal to a squared plus a squared. So that tells us that the hypotenuse squared is 2 times a squared. So that tells us that the hypotenuse is the square root of 2 times the side length a, or I often write it as a times the square root of 2. So square root of 2 is approximately 1.4. So whatever the side length is of the two legs, the hypotenuse is approximately 1.4 times that side length. That's true of all of these isosceles right triangles. The half equilateral triangle. Equilateral means that all three legs are the same length. And so that would be, this is the equilateral triangle. One length, same length sides all the way around. But we're looking at only half of that triangle. So if this is length A, then this is going to be half that length. And rather than dealing with fractions, I will generally, instead of calling that one A, I will call the shorter leg A, and that makes the hypotenuse 2A. Right? Because here's A, and this is an equilateral, so that this has to be 2A all the way around. Okay, so now looking inside this right triangle, I can use the Pythagorean theorem. We have a squared plus that missing leg squared has to equal 2a all squared. So that means the a squared plus the leg squared is 4 times a squared. So that says the leg squared has to equal 3a squared. So the leg has to be the square root of 3 times a, or I usually write it as a root 3. Okay. Oh, and the angles. So looking at the equilateral triangle, the angles in that triangle have to add up to pi. So that means each one of these has to be pi over 3. That's pi over 3. This is pi over 3. And this whole thing is pi over 3, which means half of it would be pi over 6. Okay, and again, there's the pi over 2 is the right angle. So in general, you can see like the half square triangle, or the isosceles right triangle, has these side lengths in ratio. And so like if the two legs are each 4 centimeters, then the hypotenuse is going to be 4 times the square root of 2 centimeters. And I typically, instead of using this a, and a root 2, I will generally do something like, I will just remember the ratios, and so I'll call this 1, 1, and then this is the square root of 2, knowing that all of this is going to be multiplied by some base length a. And similarly, with the half equilateral triangle, I will think of this as 1, 2, the short leg is 1, and then the hypotenuse is twice as long, and then the longer leg is root 3. And all of these are multiplied by some base side length. Okay, so here are a couple of examples for us to play with. Again, pause the video, see if you could do this on your own before you look at my answers. All right, so coordinate distance from the origin to point P, which is at 4, -4. So I'm going to look at this here. So I'm going to go 4 in the positive x, here's positive x, here's positive y, and 1, 2, 3, 4 down in the y. There's my point P, and I'm looking at this distance here. And if you look at this, you can see that this is part of an isosceles right triangle where the two side lengths are 4 and 4. And so that tells us that based on this model, the hypotenuse is going to be 4 times the square root of 2 units. And if you want, you can go through using the Pythagorean theorem, knowing that this is a right triangle here. Go through the Pythagorean theorem, do the same thing, and you're going to get 4 root 2. Okay. This one, we're given a triangle in which we have one leg is 2 meters and then the hypotenuse is 4 meters. Since the hypotenuse is twice the length of one of the legs, that means this must be a half equilateral triangle. So the multipliers are, there's the shorter leg, and then the hypotenuse is twice the shorter leg, and then the longer leg is the shorter leg times root 3. So BC has to equal 2 times the square root of 3 meters. This also asks, what is angle CAB? Angle CAB, that's one of the angles of the equilateral triangle if I extend this out. So angle CAB has to be pi over 3. This one, we have a right triangle where one of the legs is twice the length of the other leg. Now, that is not one of our special right triangles. We have the one where there's the two legs are equal, and then the one where the hypotenuse is twice the length of one of the legs, but not where one of the legs is twice the length of the other leg. And so for this, we're stuck and we need to use other means. So for example, to find FD or DF, we need to actually use the Pythagorean theorem. So DF squared is 14 kilometers squared plus 7 kilometers squared. So DF is going to be the square root of 245 square kilometers. I went and did that on my calculator. 14 squared is 196 plus 7 squared is 49. And so DF, you can pull, this is 49 times 5, it turns out. So this is 7 root 5 kilometers. Angle FDE, I know that tangent of angle FDE is going to be 2, which is 14 kilometers divided by 7 kilometers, opposite over adjacent. So I'm going to skip ahead a little bit and use the inverse tangent. The measure of angle FDE is going to be arctangent of 2. This is how to get from the ratio back to the angle. And that's approximately 1.107. Okay, so sine of pi over 6. Pi over 6 is part of our half equilateral triangle. Special right triangle, so I'm going to draw my equilateral triangle. Here's the half of it. I'm going to go ahead and erase some pieces of it. Okay, so this is the pi over 3, the pi over 6, and I'm going to go ahead and I'm going to just re-emphasize why I only remember the things without the a. So if this is a, then this is the hypotenuse is 2a, and then the longer leg is a times the square root of 3. So sine of pi over 6, that's opposite over hypotenuse. So this is a divided by 2a. Those a's are always going to cancel. Anytime I take a ratio of 2 of those sides, the a's are going to cancel. So I could have just as easily have done this with just side lengths. Here's my pi over 3 angle and pi over 6 angle, and side lengths 1, 2, and square root of 3. Remembering, of course, that the hypotenuse is twice as long as the shorter leg. Okay. Cosine of pi over 4 is, I'm going to use the isosceles right triangle or the half square. So this is going to be 1, 1, and square root of 2. Here's my pi over 4. Adjacent over hypotenuse is 1 over square root of 2. And tangent of pi over 3 is, I'm going to use my half equilateral triangle again. Here's my pi over 3 and my pi over 6. I'm imagining that other half. Here's my 1, 2, and square root of 3. Tangent of pi over 3, opposite over adjacent, is square root of 3 divided by 1, which is just square root of 3. Okay. You should not memorize the trig values on these on these types of fractions of pi. You should remember these two special triangles and what their side length ratios are. You should be able to build them from scratch with the understanding of what's going on, okay? At some point, it'll be kind of quick enough so that you can just draw this quick reference triangle with the 3 side lengths and be able to calculate all of your trig values. Okay, here we are. Defining trig values on all angles using the coordinate plane. So, given any angle theta, we put it in standard position in the plane, which means, standard position means the vertex of the angle is always at the origin, and the initial side is always in the positive x direction. That's the initial side. And then we rotate our angle. The positive rotation is in the anti-clockwise direction, and negative rotation is in the clockwise direction. This is assuming that you use clocks that run that way, and also assuming that you use analog clocks. So, given any angle theta, so I'm going to, just for the sake of cuteness, go and make a theta that goes in the negative direction and wraps around more than once and ends up with a terminal side here in the second quadrant. So that's going to be my theta. So here's the terminal side. Now, given that theta, we put it in standard position. So this is an angle that's going to be negative and bigger in absolute value than 2 pi, bigger in absolute value than even 3 pi, because a half turn is pi and a full turn is 2 pi, and I've gone 1/2 to have 3 half turns, more than 3 half turns, so that's more than 3 pi in the negative direction. Okay, so there's my theta, and I find any point on the terminal side, x comma y, any point there at all. And then when we define this, we define, for one thing, r is going to be the square root of x squared plus y squared. If you think for a minute about what the meaning is of r in this context. Hopefully you have an answer for that. I'll give you the answer in a little bit. We define the sine of theta to be y over r. The cosine of theta is x over r. The tangent of theta is y over x. The cosecant, so I aligned these up, so cosecant is the reciprocal of sine, which is r divided by y. Secant is the reciprocal of cosine, which is r divided by x. And cotangent is reciprocal of tangent, which is x divided by y. Okay, I want you to notice that this is exactly the same as our right triangle definition of these trig values. If I go and put a perpendicular line from my point to my x-axis, then the horizontal leg is essentially my x-coordinate, the vertical leg is my y-coordinate, and that hypotenuse is r. This is where r is the square root of x squared plus y squared, or r squared equals x squared plus y squared is the Pythagorean theorem. So this says I'm thinking of theta as being the angle that's at the origin. So y divided by r is essentially my opposite divided by hypotenuse. X divided by r is essentially my adjacent divided by hypotenuse, and y divided by x is opposite over adjacent. So this is exactly the same as the right triangle definition of these trig values. What else did I want to say here? I wanted to say, note that x and y can be positive or negative, but r is always positive. So that means, in this particular case, the particular angle that I drew has a positive y value, a positive r value, and a negative x value. So in this particular case, sine is going to be a positive value, cosine is going to be a negative value, tangent is going to be a negative value. Let's see. So there's also defining all trig values on the unit circle, defining trig values on all angles using the unit circle. We're going to do exactly the same thing. I'm going to have my initial side, we're going to put it in standard position. My initial side is always the positive x-axis. And then I'm going to go ahead and kind of use the same theta just for demonstration purposes. Put my theta. But here, I don't take any old point along the terminal side of theta. I specifically take the point that intersects with the unit circle. The unit circle has center at the origin and radius 1. That's what we call the unit circle. Unit essentially means 1. So I'm going to take this point at the unit circle, and I'm going to define the sine of theta to be just the y-coordinate, the cosine is going to be the x-coordinate, and the tangent is going to be the y-coordinate divided by the x-coordinate. And again, these are the reciprocals. This is going to be 1 over y, secant is going to be 1 over x, and cotangent is going to be x over y. And again, I want you to notice this is exactly the same definition, because if I drop a perpendicular to the x-axis here, make a right triangle, here's the horizontal distance is essentially my x-coordinate, the vertical distance is my y-coordinate, and what's the hypotenuse in this case? The hypotenuse is a radius of this unit circle, so the hypotenuse is 1. So the sine of theta is opposite divided by hypotenuse, which is y divided by 1, which is y. The last definition, it's good to know all of these definitions, and it's also good to know that all of these definitions are the same definition. So all of these previous ones are talking about defining trig values on all angles. Okay. Using the coordinate plane, or using a right triangle, or using the unit circle. Okay, now these angles we typically write in radian form, and radians are unitless. Okay, they're just numbers. And so I can ask, what is the sine of 45 degrees? And that is an angle measured in a unit of degrees. I can also ask, what is the sine of 45? And when I ask what is the sine of 45, I can think of that as 45 radians. I can think of that as an angle in radians. I can also think of it as a distance, and I will show you how that is. So, given any real number, basically, we can think of this unit circle as a real number line that's wrapped around itself in a circle infinitely many times. So I start here at 1, 0, and I go t along, like thinking of this as a real number line, where this is the positive direction of rotation and clockwise is the negative direction of rotation. So if I go t units, so here's my t units along the unit circle, and I end up on this point xy, then I will define sine of t to be just the y-coordinate where I ended up, cosine of t is the x-coordinate, tangent of t is the y-coordinate divided by the x-coordinate, cosecant of all of these things are the reciprocals. So cosecant of t is the reciprocal of sine t, so that's 1 over y. Secant of t is the reciprocal of cosine t, so that's 1 over x. And cotangent of t is the reciprocal of tangent t, so that's x over y. Okay, why is this the same as before, as the other values? So remember, so I am going to draw my angle here. And I want you to remember about how radians are defined. The radian measure of an angle is how many radius lengths are in the arc subtended by that angle. So here, if the radius is 1, then t, the number t, which is a distance, is the same as the number of radius lengths. So the angle theta is the same as t radians, because that distance t, since this is a unit circle, since the radius is 1, the distance t is the same as the radian measure of the angle. So all of these are the same thing. And so it basically comes down to either putting an angle into standard position in a plane and picking some arbitrary point on the terminal side of the angle, or specifically choosing the unit circle point, or thinking of this distance not as a radian measure length, but as a distance along the unit circle, and and all of these are doing the same exact thing of essentially doing the SOHCAHTOA on your a little reference triangle that you can build here. So there's my x coordinate, my y coordinate, and the hypotenuse length is 1. So opposite over hypotenuse is y over 1, adjacent over hypotenuse is x over 1, and so on. All of these are exactly the same definition. And the different definitions are helpful in different contexts. So sometimes it's a little bit helpful to use one definition or a different definition. So let's see this in action. Find the following values and draw an appropriate diagram to support each one. So here, cosine of negative 8 pi over 3. So I am going to need pi over 3s. I think of, by the way, here's a little side statement. Lots of people have printed out and tried memorizing this thing that is called the unit circle that has gobs and gobs of angles marked on it in degrees and in radians and lots of coordinates. And it's exhausting. Like, I don't actually recommend it. So I always think of anchoring on a half turn is pi. That's a half turn. Since this is 8 pi over 3, I'm going to look at dividing that half turn into 3 equal pieces. I'm going to go in the negative direction, so here's my roughly thirds of pi, something like that. In the negative direction, I go negative 1 pi over 3, 2 pi over 3, 3 pi over 3, 4, 5, 6, 7, 8. There's 8 pi over 3 in the negative direction, negative 8 pi over 3. Now, I know since this is going to be, that's going to be a pi over 3 angle there. If I make this right triangle, then this angle here at the vertex is going to be a pi over 3 angle, which means this is a half equilateral triangle. So the shorter leg is 1, the hypotenuse is 2, and the longer leg is square root of 3. And now I need the signs of these, SIGN signs. So the x-coordinate is negative here, and the y-coordinate is negative here. And cosine is adjacent over hypotenuse. Adjacent is adjacent to the angle at the origin. So this is going to be negative 1 divided by 2. Or negative 1/2. That is my picture that helps me figure out what cosine of negative 8 pi over 3 is. Okay. Sine of 11 pi over 2. So I know that this is a pi over 2, and I need to do 11 of those. So 11 halves is, this is 5.5 pies. So here's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and another half pi. So that is 11 pi over 2. And here, there's no triangle to draw, because if I draw a perpendicular to the x-axis, then I've got one leg that is going to be kind of overlapping the hypotenuse. There's no actual triangle. Okay, so here it's actually easier to go with the unit circle. And if I, this point here is the point 0, negative 1, and sine just picks out the y-coordinate, so this is going to be negative 1. Okay? So this is one place where the right, like when you get things that are like kind of degenerated to not triangles, specifically on these compass points, the the places where the unit circle intersects the axes, then you're not going to be able to use the SOHCAHTOA. But remember that all of these other definitions are kind of based off of the SOHCAHTOA. And so all of these work too. And in fact, even here, right? You know, I could put, on the terminal side, I could put I can use the point 0, -3. And in this case, r would be the distance of this point to the origin, which would be 3. And so the sine of 11 pi over 2 would be the y-coordinate, which is -3, divided by r, which is 3, which this simplifies to -1. But in general, I think it's more helpful to use the unit circle in this case. Okay, -7 pi over 4. A half turn is pi, so I'm going to divide that half turn into 4 equal pieces. And I'm going in the negative direction. So there's my quarter pies, right? And then I'm going to extend it in the other direction as well. And so I go 1, 2, 3, 4, 5, 6, 7. That's -7 pi over 4. And I end up here. And if I drop a perpendicular down, that's my half square or isosceles right triangle. So I'm going to just label these 1, 1 and square root of 2. And think about the signs. Both x and y are positive in this quadrant. So this is going to be just opposite over hypotenuse, or opposite over adjacent is 1 divided by 1, or just 1. Finally, last thing is just we're going to use the unit circle to approximate some values. One of the nice things about the unit circle, about the unit circle definitions of these functions, by the way, we often refer to them as trig functions. They're also sometimes called circular functions because some people define them without triangles at all. They just say, you know, you move so far on the unit circle, and then the sine is your y-coordinate and the cosine is your x-coordinate. And it's kind of nice, like it's basically decomposing a circular motion into a vertical motion and a horizontal motion. Okay, so the cosine is essentially your horizontal coordinate, and the sine is essentially your vertical coordinate. So here I'm going to look at cosine of 2.4 pi. Now, this is an estimate. It's asking me to approximate these values. And so this is really, it's a little bit tough. So cosine of, I'm going to try to figure out how to place this 2.4 pi. So I know that pi is a half turn. And that means I need to divide my half turn into, 5 equal pieces or 10 equal pieces? So 1, 2, I'm going to go up top. So I'm going to do something like that. I think that's roughly 5 equal pieces. 1, 2, 3, 4, 5 equal pieces. And so if I divide each of those pieces in half, then that's basically tenths. Going around, I would go, here's 2 pi, 2.1, 2.2, 2.3, 2.4 pi. That's 2.4 pi, roughly. Now, in this place, I'm going to go ahead and drop a perpendicular, and I'm going to, since I have a rule, I'm going to just use the y-axis to kind of eyeball a parallel. And same thing here, using the x-axis to eyeball a parallel. And it looks like my x-coordinate is around 0.123, 0.31. And the y-coordinate looks like, I don't know, 0.96, 0.95. Just kind of looking at where those coordinates are on the axes. The cosine is the x-coordinate, so I would say it looks like this is approximately 0.31, based on what I can see here. And it turns out I looked at the calculator, and cosine of 2.44 pi is actually about 0.309016, which is like, I'm shocked that my eyeballs got that accurate of a number. I'm sure that won't happen with this other one. Okay, sine of -7. So I'm using the fact that like pi is approximately 3.14, so that means that 2 pi is approximately 6.28 or 6.3. So that means -7. So this is about -6.3, and then if I go another 0.7 along. So I'm going to think about, here is a 0.7 distance right there, and I'm kind of going to mentally think about going that same 0.7 distance. Maybe there. This is 0.7. So I think that this would be approximately -7 as a radian measure angle, or thinking about, all the way around the circle, the unit circle, going around once would be about 6.3, and then there's another 0.7. So, again, I have my x and y coordinates. I'm just going to take and see if I can eyeball a line that's roughly parallel to the y-axis in both directions. And the sign here is the y-coordinate. I'm going to go ahead and say this is the x-coordinate looks like it's about 0.62, say, and the y-coordinate looks like it's around -0.76. Okay, so based on my picture, I got that sine of -7 is the y-coordinate here, which would be -0.76. Okay, and using my calculator to actually calculate the sine of -7, where -7 is in radian measure, I get the sine of -7 is approximately -0.66, so I was off by a pretty large margin on there. But the idea of this is really to kind of get accustomed to like the meaning of the radian measure and the meaning of the trig value, so that you know that like when you're using the unit circle, cosine is reading off the horizontal component or the x-coordinate, and the sine is reading off the vertical component or the y-coordinate.